I want to do one that has a pin and slot joint. It's the same way you would treat something with a roller. So let's say that there is so a vertical wall and it looks like this, and the slot is vertical like this. Okay, let's say that this angle is 10 degrees at this instant. And let's say there's a force being applied to the pin connecting the two there. So let's say that's 100 newtons. The masses of these two bodies, let's make all this the same. So let's make the mass 1 kilogram and the length 0.5 meter. And just to make the math simpler, we'll start with both of the angular velocities equal to 0. And we want to calculate the acceleration vector of the pin in the slot. Okay. Let's start out by numbering the members. I'll call it 1 and 2. I'll call these joints A, B, and C. And so to start with, we're just going to do the rigid body analysis of the two bodies. So body 1. Well, let's instead of me just going through this, let's do it the way we did last time. So we'll kind of do it piece by piece, and I'll let you work on these things. So go ahead and do the rigid body analysis of body 1. Okay, so body 1. Does it have a fixed point? Yes. And so we're going to have to use the parallel axis theorem for the moment of inertia. And so this is equal to 1/12 times the mass times the length squared plus the mass times the distance squared that you have to move from the center of mass to the about point. So this is 0.25 squared. And I think you get 0.083 repeating. And now the free body diagram. We have an unknown reaction force up here. I'll call that RA. We have a weight at the middle. That is 9.81 newtons. Here we have the reaction force on 1/2. And then what about that 100 Newton force? Does that show up here? Yeah, I mean, you can put it on either one of those two members. If you look at that question and something about the picture suggests to you that that's actually applied to member 2, then that's fine. The answers will all come out the same in the end. You just don't want to double count that force. And what I use to keep stuff straight is anything that happens at the joint, I treat it as happening at the lowest numbered member at that joint. So since that joint connects members 1 and 2, I treat that 100 like it acts on member 1 and not on member 2. Okay, so I also have this 100 Newton force like this. And then the table. Our about point is here at the pin. So I'll start with RA, the row vector. The definition of the row vector is the vector that goes from the about point to the point where the force is applied. Cross product is 0. And then we'll go to the weight force. And the row vector for that in the x direction is 0.0208. And in the y direction is negative 0.24. What am I doing here? Oh, I copied the wrong thing here. This should be 0.043. And this one is 0.246 negative. Is that what other people got? Yeah. Okay. And then the force vector is 0, negative 9.81. So the cross product is 0.426 negative. And then the force F12. That is the row vector 0.087. And the x component, the y component is negative 0.492. The force is F12x, F12y. And so the cross product is 0.087 F12y plus 0.492 F12x. And then last is that 100 Newton force. That is the same row vector as F12. Bless you. The force vector is negative 100, 0. And so the cross product is, that should be negative 49.24. Anybody get anything different for any of those? Okay. This has a fixed point, so Newton's second law or no? No. So the moment equation says negative 0.426 plus 0.492 F12x plus 0.087 F12y minus 49.24 is equal to 0.083 repeating times alpha 1. And so the first equation says 0.492 F12X plus 0.087 F12Y minus 0.083 alpha 1 is equal to positive point, what did I do there? (49.24) plus 0.4. This should be 49.67. Everybody with me on that one? Okay, so next, member 2. So go ahead and do that. So the acceleration of the point C relative to the center of mass of body 2 is alpha cross r plus omega cross quantity omega cross r. Our alpha vector is 0, 0. What's the third component here? Alpha 2, that's right. Our omega is zeros. That was given at the start of the problem. That has to be given. And then our r is the vector from the center of the circular motion, that about point in the middle, center of mass, to the point C. So that's negative 0.043 and then negative 0.246. So the acceleration of the point C relative to the center of mass is 0, 0, alpha 2 crossed with negative 0.043, negative 0.246, 0. The other stuff goes away. And so this is 0.246 alpha 2, negative 0.043 alpha 2, then 0 for z. The total acceleration of that point C, then you have to use the relative motion equation. So this is 0.246 alpha 2 plus a2x, negative 0.043 alpha 2 plus a2y. That's an expression for the acceleration of that point. Now, the constraint that we want says that there's no horizontal acceleration of that point. And so we'll just take the x component of that, and our fifth equation says 0.246 alpha 2 plus a2x is equal to 0. Okay, Any questions about that? I'll finish this problem next time, but the other constraint, you've seen that stuff before, and then we'll just have to solve the big system of equations. Any questions before I turn this off? Okay, that's all.